Title of the work is Toughness and Thermal Stability of Carbon Fabric Epoxy Composite filled with 2D hexagonal boron nitride and molybdenum disulfide particles. Carbon fabric reinforced epoxy composite usage increasing in aeronautical, railways, automobiles, marine and stiffener for civil structures. CFREC has excellent strength, stiffness, light and weight. Moreover, their properties can be tailored. However, high cross-linking of epoxy leads to brittleness, low toughness. This causes premature failure under load-bearing application. Improving toughness of CFREC required for high performance application for better structural integrity. Second concern with epoxy resin composite is that it experiences thermal degradation at high service temperature. Developing a composite of higher toughness and thermal stability without compromising stiffness, strength, glass transition temperature is a challenge. This motivates for more detailed study in this research domain. Hexagonal boron nitride and molybdenum disulfide are the two fillers selected in this study. Influence of hBN and MoS2 on pure mode 1 toughness and mixed mode 1 and 2 toughness, microhardness and thermal stability of CFREC investigated. The resistance exhibited by composite in crack opening tensile and combination of tensile shear modes quantified through critical stress intensity factor as per ASTM D5045 and E1820 standard. Fracture morphology of toughness composites examined using scanning electron microscope to understand toughening and failure mechanism. Temperature withstanding ability investigated through thermogravimetric analyzer in a nitrogen environment. Figure 1a shows pre-cracked single-edge notched bend specimen for mode 1 case. Here pre-crack present at the center. Figure 1b shows pre-cracked specimen for mixed mode case. Here pre-crack present at offset distance from the center, thus causing asymmetric loading on the specimen. Picture shows 3-point bending machine used for toughness test. Pre-cracked SEM specimen supported at both ends and loaded at the center. Morphology of hexagonal boron nitride and molybdenum disulfide at various magnification can be seen. Obtained through high resolution transmission electron microscope. Most hBN particles are in discs and few are in flake. MoS2 resemble thin sheets. Flowchart indicates steps involved in composite preparation. Table 4 indicates constituents weight percentage. Figure 4a shows force versus displacement response of hBN filled CFREC and 4b of MoS2 filled CFREC in mode 1 test. The highest slope is noticed for 6BN CFREC. The stiffness of filler loaded CFREC is higher compared to neat composite. The increased stiffness and toughness are attributed to uniformly dispersed high modulus filler in the matrix. Interestingly, stick slip pattern detected beyond peak load attributed to unstable crack propagation in composite. The highest KIC of 23.62 MPa square root meter obtained for 6 MoS2 CFREC. KIC improvement is due to better filler interaction with epoxy arrest crack propagation smoothly. This shows fracture morphology of various composite in mode 1 toughness test. Crack developed in the matrix propagate leading to fiber dislodgement. Shear cups represent brittle failure of neat composite. Multiple crack dislodged matrix around fibers. Due to this, fiber disintegrates from matrix. This evidence supports the lowest KIC of neat CFREC. 6 MoS2 CFREC reveals improved fiber matrix filler interfacial bonding compared to neat CFREC. Carbon fiber failure demands more energy to fracture. Fracture morphology of 6BN CFREC depicts shear and bending of carbon fiber. hBN particle in the epoxy matrix cause obstruction to crack propagation. Force versus displacement behavior of mixed mode test represented in figure 7a and 7b. It is evident from the graph. Stiffness and peak load of BN loaded CFREC higher compared to MoS2 loaded CFREC due to the higher stiffness of hBN. The abrupt load drop in 8% filler loaded CFREC indicate brittleness of composite. The maximum stress intensity factor K1 and K2 of 7.22 and 1.62 MPa square root meter obtained for 6BN CFREC. Matrix fracture, fiber shear fracture and shallow cup in neat CFREC reveals contribution of mode 2 load. Fiber pullout in 6BN CFREC indicates crack inability to propagate in tough hBN dispersed epoxy. Hackle pattern indicates violent stage of fracture and thus 6BN CFRE represent tough composite. Intact carbon fiber MoS2 dispersed epoxy responsible for better toughness of 4 MoS MoS2 CFREC. Thermal mass stability and decomposition kinetics of each composite studied. Figure shows weight loss as a function of temperature. Filler addition to CFREC improves onset and transitional degradation temperature. Neat CFREC exhibit 25% weight loss at 395 degrees centigrade, 4 MoS2 CFREC at 430 degrees centigrade, and 4BN CFREC at 411 degrees centigrade. This indicates increase in degradation temperature of 4 weight percentage filler added composite. 4 MoS2 CFREC achieves highest thermal stability due to improved MoS2 interaction with epoxy and heat reduction due to lubricant property. Improved thermal stability of 4BN CFREC attributed to carbonaceous char formation and impermeable characteristics of hBN causes tortuous diffusion path for gas molecule. 65% improvement in mode 1 stress intensity factor witnessed due to 6 weight percentage MoS2 addition. 6 weight percentage hBN addition to CFREC exhibited 2 times improvement in mixed mode stress intensity factor. Toughness improvement was due to hBN and MoS2, which strengthen the matrix, deflects crack path, and impart resistance for crack propagation. Addition of 4 weight percentage MoS2 or hBN in CFREC improved decomposition temperature by increasing activation energy. Developed hybrid composite have multiple desirable properties useful for high performance applications.